So, welcome to our class of fermentation technology. In earlier classes, you studied about the batch fermenter and the fed batch fermenter. So, in batch fermenter, we told it is a closed system because we are adding all the ingredients, and finally, the product which is formed is recovered after a particular fermentation period. Whereas in fed batch, we told it is a semi-closed or semi-open. Here, what we do is that we add the nutrients or the cell culture at a particular interval of time, okay, or in an increment manner, but we do not remove the effluents. That is known as the fed batch culture. In continuous fermentation, what we mean is that continuous culture is to keep the culture growing indefinitely. That is, you're keeping your microorganism, you're allowing your microorganism to grow indefinitely. This can be done by continuously supplying the fresh nutrients, and simultaneously accumulated cell and the waste products are removed at the same rate. So this is known as continuous fermentation. So it is an open system to maintain a cell in a state of balanced growth by continuously adding the fresh media and removing the culture media at the same rate. So why are you doing this? What is the purpose? The purpose is that the continuous culture is to keep the culture growing indefinitely. That is, I wanted to grow the cells indefinitely in the exponential growth. You know that the exponential growth is the where many of your microorganisms are undergoing cell division. They have become metabolically active, they consume all the nutrients, and there is no shortage of nutrients there because you're continuously feeding them, and there is no question of toxicity because all the toxic materials or accumulated cell is removed. So the exponential growth phase of an organism is prolonged by addition of the fresh medium to the vessel. So this is the definition for the continuous fermentation. So if you look at a simple fermenter, this is the chemostat, which is a fermenter. In steady state, whenever we tell continuous fermentation, why we do continuous fermentation is because I want a steady state growth, which is not possible in the batch fermenter. What is the steady state growth? You know that I'm going to keep my cell in the exponential phase itself. So this is your fermenter, and this is the media reservoir. If you want to pass your media into the fermenter, and this is a vessel which collects your effluents. So in steady state formation, what happens is the new biomass, okay, whatever the new biomass is what? The microorganism. The formation of new biomass is equivalent to the loss of cell from the vessel. So whatever the new biomass is being produced is equivalent to the loss of cells from the vessel. So what is the meaning? What is this new biomass? New organism is formed. How? Because you are pumping in the new media, and this is equivalent to the loss of the organisms which are being removed from the fermenter. So this is called as the steady state because there is an equilibrium there. So the media flows into the vessel is related to the total volume of the media within the vessel as the dilution rate. It is known as the dilution rate, which is represented as the D. Once again, I'll repeat, the media that flow, okay, this media that flow into the vessel is related to the total volume of the medium within the vessel as dilution rate. It is represented as D. Now, what sentence I told, I can express that as mathematically in a mathematical equation. That is, D is equal to FV. So, where D means it is the dilution rate, okay, of that fermenter. and F is the flow rate, whatever the inflow of the fresh media, which is the decimeter cube per hour. V is the total volume in your fermenter. So the net change in the cell concentration is equal to the growth minus output. That is what the starting we told in steady state formation of new biomass is equivalent to the loss of cells from the vessel. So there is a net change in the cell concentration because new growth is happening minus output. That is, some of the cells have been removed from your reservoir or your fermenter. So that I can represent it as dx by dt. What is dx by dt? It is the net change in the cell concentration is represented as dx by dt is equal to growth. That is mu x minus output dx. So the steady state mathematical expression under steady state condition, always your dx by dt is 0. Okay. So the equilibrium becomes mu x is equal to dx, which in turn will become mu is equal to d. So this is called as a steady state or the stable state. Why it is called stable means it is due to the self-regulation. Okay. So remember, this phenomena is called as a steady state because it is stable. Why? Due to the cell regulation. So what do you mean by mu? Mu is, you have already read it in the batch culture itself. It is the growth rate of the microorganism. And also you read about another term mu max, which is the maximum growth of the microorganism at a given substrate. So that is not required now. Just we have to remember x. X means it is the growth rate of a considered microorganism. So steady state means it is a net change in the cell concentration equal to the growth minus the output. So steady state will be developed at a dilution rate when the equal to the outflow rate divided by the volume. This one. Okay. So this is what F is what it is the flow rate equal outflow rate. V is the total volume. So everything remain constant in your continuous fermentation. So your culture volume, your dissolved oxygen, nutrients, product, concentration of the pH, temperature, cell density, everything remain constant in continuous culture. This is called as a steady state because these are all whatever I mentioned now, the dissolved oxygen or nutrient, your product, your pH, cell density, culture volume, all these are stable due to self-regulation. So hopefully you understood now what do you mean by steady status. So it is the state, the cell growth at a level at which the productivity is optimum. That is the objective of our continuous culture. The control cell growth at a level at which the productivity is optimum. So we have two types of continuous fermenter. One is the chemostat and other is the turbidostat. So you usually in the end of the class when we are talking about the advantages, I'll tell you this temperature and pH, all whatever I told, they have to be all in optimum value because these are very important for your primary and secondary metabolite production of the microorganism. That is why it is very important. Okay, you have already studied about the primary and secondary metabolite of the microorganisms. So if have to get these primary and secondary metabolites, the temperature, pH, and other factors what I have mentioned should all be in the optimum. That is why it is called as the productivity should be optimum. Then what is chemostat? Its chemostat is a type of continuous fermenter. So here what you do is cell growth is maintained steadily by a constant inflow of fresh media. Fine. With nutrients like nitrogen, phosphorus, glucose at a concentration that limits their growth. So what you're doing, you're providing all the new nutrients, fresh media you're providing. But what you're doing, the nitrogen, phosphorus, glucose, which is essential for your growth of the microorganism, one of the nutrients, you are limiting their growth. And other constituents are present at the concentration higher than required. So one of these nutrient will be in the limits. That is, it has a limited growth. Now, what is the purpose of this? So, here you can see the purpose. Increase or decrease in the concentration of growth limiting factor. What is my growth limiting factor? It is your nitrogen, phosphorus or glucose. Increase or decrease in the concentration of the growth regulating factor is correspondingly expressed by the increase or decrease in the cell rate of growth rate of cell. So what happens is, if you are increasing or decreasing the concentration of either nitrogen, phosphorus or glucose, which is actually essential for the growth of the microorganism, if you're limiting this factor, that is, you are either increasing or decreasing in the concentration of the growth limiting factor, it is correspondingly it expresses an increase or decrease in the growth rate of the cells. Cells means your microorganisms. So you can see the interconnection between these two. You increase or decrease the concentration, that correspondingly increases or decreases the growth rate of your cells. So the volume of the chemostat can be controlled by using a pump. Okay, because this is very important, because I should know which nutrients I should limit, so that that particular microorganism's growth rate can either increase or decrease. Okay, so here what is means, everything should be in the exponential phase. That is, everything should be in a multiplying phase, or they should be in log phase. See, one going at a faster rate and one going at a slower rate, what happens? There is no uniformity. That is why we limit the nutrition. So all your organisms, okay, suppose say this is one organism, this is another organism, this is another organism, they are not in the uniform stage, they are not exponentially uniform. Okay, they are not in a steady state. To bring them everything to in the steady state, you have to limit any of the nutrients. By limiting the nutrients, you can, limiting means you can increase the nutrients or decrease the nutrients. By doing so, indirectly, not indirectly, directly, you are increasing or decreasing the growth rate of the cells, and that can be controlled by yourself. Whoever the person is in that fermenter, he can control it. So this is what is the chemostatus. Okay, and this is the outflow of the media and the cells, and here it is the inflow of the media from here, and here the fermentation occurs. So here this is the steady state is maintained. That is, how much of my new organism is formed, new biomass is formed, is equal to the number of the outgoing organisms. So here also you can see an example of a chemostat. See, the medium fed in the constant rate, this dilution rate determines the mu. What is the mu? Mu is the growth rate of the organism. Whichever organism you have considered, that is known as the mu. So the medium fed in at a constant rate, this is the dilution rate. This dilution rate, what it determines? It determines the number of the cells, the growth rate of the cells. So all nutrients cells are in excess except for one limiting nutrient. So that phosphorus, nitrogen, and one more what we spoke was glucose. So these are the limiting factor. So any of one of them can be a limiting nutrient. All nutrients are in excess except for one limiting nutrient. And this is the surface medium, and simultaneously the culture volume kept is constant by overflow of the harvest device. So this culture flow is kept constant because the rate here, how much ever is flowing out, here the rate is equal to the inflow. So this is the dilution rate, which is determining the growth of a organism. So one of the factor, one of the nutrient I'm going to limit. So whether I'm increasing or decreasing the nutrient, it has a direct effect on the increasing or a decreasing of that particular microorganism. So the record of biomass concentration X, okay, and the substrate glucose concentration S over the early stages of cultivation, showing the transition from the initial batch phase to the continuous phase. So here what is X? It is the biomass concentration, and this is your glucose concentration, your capital S. Okay, and over the early stages of cultivation, showing the transition from the initial batch phase to the continuous phase. That is, what is happening is they are moving from the batch, your microorganisms are moving from the batch phase to the continuous phase. So batch phase means you have all the four growth curves, but here it is just your exponential phase. Okay, so you see here, this is your batch phase, and your medium supply turned on at D cells, then mu. So here what you're doing, medium supply is turned on. You're turning on the medium, fresh medium you're going to add, which is known as the dilution rate, okay, which will determine the number of growth organism mu here. So continuous culture is established. So I'm adding fresh media. You are batch phase, right? So what I'll do, I'll add the fresh media. What will the fresh media will do? That will be your dilution rate of your growing microorganism. Meantime, what happens if I'm adding the fresh media? Continuous culture is established. That is, exponential growth phase is prolonged. Okay. So it is prolonged based on the concentration and the substrate concentration. Both are important. That is your biomass, your microorganism, and the substrate on which your microorganism feed. That will determine the transition phase from the batch phase to continuous phase. Hope this is clear. Okay, so we are particularly in continuous culture, we are seeing to that we are adding fresh media each time, so the new biomass is being produced. But in other fermentation, that was not the case, right? Why I'm producing this, always putting the new biomass? Because I want to keep my culture, everything in the exponential phase. So what is the importance here? The importance is the biomass concentration, that is the microorganisms, and even the substrate is important, because fresh substrate I'm adding, then this organism can consume this substrate, okay, and it can start dividing. So from batch phase, it is moving into a transition phase, which is the continuous culture phase. So you're adding fresh media, my microorganism can consume that fresh media, and simultaneously what you're doing is the volume is kept constant by overflowing overflow the harvester devices. That is, whatever is being produced, you are harvesting. That is what is the chemostatus. You are limiting one of your nutrient. And this is the graph which is showing that from batch phase it is moving to the continuous culture phase. And what is important? The biomass concentration and the substrate is important. So the very important parameters is the temperature and the pH. They should be kept constant at optimal level. So the pH and their even the temperature are monitored, and liquid flow rate is automatically adjusted to maintain the variable at a constant level. So this is all, you have to maintain a constant level, this pH and temperature, all this. Next, coming to the turbidostat. So this is also a culturing method. But here, the difference between chemostat and turbidostat, in chemostat, you're limiting one of the nutrient. Here, there is no such limiting at all. Turbidity of the culture is held constant. Okay. Suppose say, how will I measure the turbidity? I'll take small amount of the culture and keep it in the spectrophotometer. For example, the spectrophotometer gave me a reading of 0.7. Okay. That is the optimum what I want. So the turbidity of the culture is held constant by manipulating the rate at which the media is fed. So here we are manipulating what? The rate at which the media is fed. So I see to that whatever the new feed or the fresh feed I am providing, it should retain this 0.7. For example, I am telling 0.7. Okay. So what I should manipulate? The rate at which the media is fed. This rate I should manipulate. If the turbidity increases, feed rate is increased to dilute the turbidity back to its set point. What it means to tell is, suppose say it becomes 0.9. So it is not optimum. So I should bring it to 0.7. Suppose say if it is 0.5. No, it is not optimum. I have to bring it to 0.7. 0.5 means the turbidity is very less. That is, microorganism is not growing as I thought of. Okay. So what happens? I should manipulate the rate of medium, add more of the medium so that it reaches the 0.7. Here what I can do, I can reduce the rate of media so that it comes to 0.7. This is the turbidostat. Okay. So I am maintaining the turbidity. What is turbidity? It is your microorganism there. The turbidity of the culture is held constant by manipulating the rate at which the media is fed. Whether I have to increase the media or whether I have to decrease the rate of the media to achieve the optimum turbidity. So coming to the type of continuous fermentation, there are different types of continuous fermentation. So you have to remember a very important point, that is, the continuous culture device are means for maintaining cell population in exponential growth factor. This is what is the main important point in your continuous culture. Okay, that means of maintaining the cell population in the exponential growth factor for long period. The rate at which the culture is diluted is governed by the growth rate and the yield. So we are keeping everything constant, but the dilution can be variable, because if I want to, whatever we saw, the manipulation what we are making with the dilution. Okay, so that only that will be a variable factor here. So under the steady state condition, specific growth is controlled by your dilution rate, which is a controllable variable. That is why your dilution rate is very important. Okay, so your dilution rate, what we told, TF by V, right? This is the dilution rate, right? So what did we tell? Continuous culture fermenter means it is a steady state. Okay, because the growth is the growth minus output, they are uniform. Whatever the number of cells is produced, the same number of cells is being removed. That is the steady state we told. So thus under the steady state condition, specific growth is controlled by the dilution rate. You control your growth of microorganism by varying the dilution rate. So others all are constant. Your pH is constant, your temperature is constant, your culture is constant, the density is constant. Okay, but you can vary your dilution factor or dilution rate. It is a controllable variable. Only this is a variable. So in continuous culture device are means for maintaining the cell population in the exponential growth factor for long period. The rate at which the culture is diluted and govern the growth rate and yield. So this dilution rate is the one which governs the or controls the growth rate and the yield. Hope it is clear. So I am in chemostat, everything is I am maintaining in the steady state. That is what you have to remember. And only your dilution rate is a variable one, because it is the one which is governing the growth rate and the yield. So type of continuous fermentation: single state continuous fermentation, multiple, recycle and semi-continuous. So single state continuous fermentation means entire operation is carried out in one vessel. Nutrient is added simultaneously with the broth outflow. Suitable for the growth related fermentation like yeast, alcohol, organic acid production. Multi-stage continuous fermentation, it is a battery of fermentation. So here one fermenter, here another fermenter, here another, like this. A battery of fermenters will be present. Okay, the medium is fed into the first fermenter tank and the outflow into the second, third and fourth tank, as the case may be, how much ever the fermenters are there. So the first one is used, it is used for fermenting involving metabolites. So the first tank may be used for the growth phase. In the first tank, you use for the growth of your microorganisms. Okay, so first, second, third and fourth. So in the first, what you're doing, the tank is used for the growth phase of the microorganisms, and other tanks are what? It is used for the production. Okay, depending on various requirements identified for maximal productivity, because this is particularly used for the metabolites production. Different primary or secondary metabolite production, we are using this. So the first one, what you are doing is you are using it for the growth phase of the microorganisms, and others all you are using for the production or the final stage productivity. Okay, all the metabolites should be produced. So that depends on various requirements. Okay, whether you require one fermenter, two fermenter, three fermenter, it depends. That is why it is called as multi-stage continuous fermentation. A recycle multi-stage continuous fermentation. Here what happens is outflowing broth may be freed from the microorganisms. Okay, my broth, it is freed from the microorganism. The broth is free from the microorganism. How? By centrifugation. And what did I get? I got it the supernatant. I got this supernatant in return. I separated my broth, I separated my microorganism by using centrifugation, and finally I got a supernatant, a clear supernatant. Now, particularly useful where the substance is difficult to degrade or not easily miscible with water like hydrocarbons. So the supernatant, whatever I got, I returned back to the system. System means your fermenter. When this is used is particularly useful where the substances is difficult to degrade. Okay, it is not properly able to degrade the substances because they are not easily miscible, because we would have added certain solvents which are not miscible with each other, otherwise are immiscible. For example, water and hydrocarbons. Okay, so that is why it is called as recycle single or multi-stage continuous fermentation. You can use the same like multiple stage of fermenters, but you have to recycle your supernatant each time. And cyclic continuous fermentation means single series of vessel may be used. Fermentation proceeds to completion or near completion and volume of the fermentation broth is removed. So after you have removed your broth, after the fermentation is complete, fresh media of equivalent volume is then introduced into the vessel. So this is a continuous cycle which is happening. However, the productivity is lower than the continuous fermentation. It is lower than when you compare with the actual continuous fermentation. Then the cell reuse fermentation. Cells are centrifuged from the fermentation broth and used to re-inoculate the fresh media. So here what happens? I have my media. My media is having the culture. I again separate them by centrifugation. So the culture is, what do you mean by culture? Culture is nothing but your microorganism. I take that microorganism and add it to the fresh media. I add it to the fresh media. Again, this fresh media, what I'm going to do? I'm going to add it into the fermenter. So what is happening? The volume, okay, the volume of your organism, that is your volume of your microorganism is going to increase here. Okay, so this was your media. This is your media. And this is your culture. What is your culture? It is a microorganism. So what did I do? I separated them by centrifugation. I separated. So whatever the microorganism I got, I put it into the fresh media. I put it back to the fresh media. And this fresh media, it is again entering into the fermenter. Okay, or the tank. That will be more simple to say. Fermenter tank. So as this is entering, what happened? The volume of your microorganism is increasing. Already there is microorganisms. Again, you're adding microorganisms. So the volume increases. It is continuous only in the sense that the cells are reused. Otherwise, it is a batch fermentation. Only if the cells are reused in this manner, it is called as a continuous phase. Otherwise, if it is not reused, it becomes like a batch fermentation. So what are the application of your continuous fermentation? It has lot of applications. For example, it is used in the single cell protein production, ethanol, acetone, butanol, isopropanol, acetic acid. Okay. These can be produced from your sugar, starch, molasses, cellulose. Okay. Many of the raw materials are there which can produce whatever I told, that single cell protein or ethanol, isopropanol. Okay, it is used in the production of cheese, yogurt, lactose, whey, you know, that liquid part of the milk. Okay, and it is also used in the production of vaccine, cell cultivation, sewage, treatment of sewage, chemical waste, and it is also used in the brewing industry for wine, beer and wine production, vinegar production. So it is having a lot of application if you look into it. So that is about your continuous fermenter. So here, if the media is fed continuously to the batch culture at a suitable rate, then the steady state is achieved.